All right, so let's circle back to the sort of the original image that I showed at the beginning of the previous video, which really just showed three different physical states of matter, where we had gas, we had liquid, and we had solid. And so we just kind of covered the different flavors of intermolecular forces and said, well, those are the actual forces that are holding molecules amongst each other. They're not the bonds that hold the molecule or the atoms together in the molecule. They're just the things that molecules have that interact with each other. So when we think about gases, we really just say, well, those things are essentially infinitely far apart from each other. So we don't think about intermolecular forces with gases. They're really, really far apart. So intermolecular forces are largely the dominant things that cause solids to hold molecules in a distinct crystalline lattice, or liquids to be close to each other, but not so close that they're held rigidly as a solid. So that type of interaction, those intermolecular forces, give rise to properties of liquids that I think we are really familiar with, but maybe we've never thought about what gives rise exactly to those phenomena. And one of those properties is this thing called viscosity. So the viscosity, I think we have an intuition of thinking about, say, like pouring syrup versus pouring water. Those things, one is really thick and the other is less thick. So viscosity is really, from a chemistry perspective, it's defined as the ease of movement of molecules. And it should hopefully be familiar then that really these properties are largely impacted by how those molecules are sliding past each other in the solution. And that ease of movement, how well they slide past each other, is largely dictated by, well, what is the force of interaction between those molecules, right? So the viscosity is directly linked to the strength of those intermolecular forces. A weaker intermolecular force means low viscosity. So on this sort of infographic that I grabbed from the internet, this side would be weaker. And for stronger intermolecular force, we have this side of things, where we have really, really viscous types of interactions. And so this is a function of the shape of the molecule, but then specifically what types of bonds are present, because the types of bonds that are present dictate what types or flavors of intermolecular forces can be present. So another property of liquids that's highly dependent or almost exclusively dependent on the intermolecular forces between the molecules is this thing called surface tension, which again I think we have some intuition, but maybe we've never actually correlated that with the intermolecular forces. So what I have are two sort of photos here. The one on the left is a picture of water on a waxed surface. So maybe this is water on a freshly waxed car, or this is water on one of those car windshields after they've applied this stuff called Rain-X, and the water beads up, right? So if we were to look at the water droplet in a side or a silhouette type profile, what we'd see are water molecules that look like that, or beads of water, not molecules, but beads of water that look like this. And then on the right, we have something like water on a vehicle that hasn't been washed in a while. It's certainly not waxed. And you can see that in profile, then we start to have water droplets that look like this. This phenomenon is what we call surface tension. So it's the differences in intermolecular forces of the interior substance versus the surface. In other words, the forces that are holding water together to form this droplet are very different than the forces on the surface. Or in other words, if we sort of peel back a layer of abstraction, it means that the sort of dipole-dipole, or the hydrogen bonds inside this molecule, are very, very different than the molecular structures of the surface, right, in this picture to the left. In the picture to the right, what sort of interactions do you think are happening? Well, hopefully you can see that water hasn't changed, right? So you still have H bonds that are holding water together, but it means that this surface now has intermolecular forces that more resemble the H bonds within water, which means that there's another intermolecular interaction between the water and the surface. We call this process here wetting because it looks like the water is spreading out and wetting across the surface. And so if you have like a polar surface, then water is going to spread across it more easily, simply because its hydrogen bonds are going to interact with the hydrogen bonds of the polar surface, or the dipole of the surface. If you have a surface instead that's very nonpolar, now you have hydrogen bonds which are highly polar, and they're interacting with a nonpolar surface. That interaction is not going to occur, which causes the water to bead up and want to get closer and closer to itself. Right? It doesn't like the surface, so it's just going to only interact with itself inside this. This is the origin of surface tension.